I hope you enjoyed all the amazing talks that already been taken today, and thank you for sticking around for this talk. My name is Eyal Trabelsi, and today I'm going to talk to you about practical techniques to optimize your Pandas code. If you have any questions, write them down and we will get to them in the end of the talk. Few things about myself. I'm a software engineer at Salesforce. I have big passion for Python, data, and performance optimization, and you can find me in Medium and in Twitter. My goal for today is to show you that optimizing your Pandas code is not rocket science, and that everyone can write optimized Pandas code without breaking a sweat. Today, I'm going to go over a few things. Why should we even care about writing optimized code? And when? And I'm going to go over some tips to improve your Pandas performance. So why we should even care about optimizations and performance? We want our code to be fast, whether we mean it in terms of latency and throughput. We want our program to have as small memory footprint as possible. Most of us are terrified of out-of-memory errors or our AWS bills. And even if we are willing to pay to improve our performance, hardware will only take us so far. But before we optimize our code, there are a few things we need to make sure of. We need to make sure that the change is actually needed, as optimized code tend to be harder to maintain, buggier, and more brittle. So we need to gather the requirements, the SLAs, the SLOs, in order to understand the user need. Also, we need to make sure the code is well tested. It will be sad if we fix the performance problem, but the output will be simply wrong. And when we optimize the code, we should only focus on the bottleneck itself. Today, I'm going to use a 1 million row dataset of meal invoices. As you can see here, we have the date, we have price, and we have a few more columns. And now for the $1 million questions, how can we optimize our Pandas code? Before I begin, it's important to state that all these optimizations depend on the size of the dataset. And for smaller datasets, these optimizations might be irrelevant. The first tip is to only use what you need. For many use cases, you don't actually need the entire dataset. You can keep only the columns that you need and only the rows that you need. And it will reduce both your memory footprint and execution time. So you should filter as early as possible. The next obvious tip is you shouldn't reinvent the wheel. There is a vast ecosystem and you should use existing libraries and solutions. They have fewer bugs and they are highly optimized. So for example, instead of implementing our own k-means algorithm, we should use SciPy implementation. The next tip that I'm going to cover is to avoid loop. And this I meet every single week. So Panda is designed for vector manipulation, which make loop inefficient. A rookie mistake in Pandas will be to just iterate over all the rows using iter rows. As we can see here, we are iterating row by row and calculating our new column by subtracting each row. We can see here that it takes 21 minutes to execute using the timeit module I measured it, and it's simply unusable. So I'm going to show you a better option, which is to use the apply function. The apply function takes a user-defined function which transform or aggregate the data frame and return a data frame as a result. So here we take our data frame and we simply do this calculation, and we can see that it only takes 8 seconds now, which is 150 times improvement in execution time, which is insane. But it's not enough. There is a much better way, which is to use vectorization. Vectorization is the process of executing an operation on the entire array at once. Pandas, NumPy, SciPy, and all these include a lot of vectorized functions from mathematical operations to aggregation. And I will show you here an example. So this minus sign is a vectorized function of Panda, and you can see that it only takes 4 milliseconds to execute entire row, which is a 2000 times improvement from the apply function. And you can create your own vectorized functions using NumPy vectorized decorator. The next step that I'm going to cover is to pick the right type for our pandas columns. I will show you the motivations. So let's say we have an array with only ones. If I give it different type for this array, we can see that the memory footprint is much bigger for object than for the other types. So we should aim to pick the type that has the lowest memory footprint but doesn't lose precision for our cause. So I will go over briefly the supported types. We have ints, we have floats, we have booleans, we have objects, we have dates, time deltas, and some more advanced types like category, which is great when most of the array include the same value over and over again. Sparse type, which is great when most of the array is null. And nullable integers and nullable booleans if we have a few nulls and we don't want the entire array to be cast as a float. In addition, you can create your own type, and there are some open source ones like CyberPandas for IP-like objects and GeoPandas for spatial objects. So let's see where do we stand in terms of memory footprint. So our data frame is 480 megs, and we can see how it's distributed across different columns. If I'm going to optimize our type using casting, we can see that now it's only 36 megs, which is 13 times improvement in memory footprint, which is amazing. In addition, optimized types give us better performance optimization for mathematical operations. The same operation on an object type and on the flow type will take much faster than the object one. We can see that the object one take 46 milliseconds, and when we cast it to float, it's only 90 milliseconds, which is 2.5 times performance improvement. The next step is to install the recommended dependencies in Panda documentation. So the first recommended installation is num expression, which is a NumPy evaluation engine, which uses multiple cores as well as smart chunking and caching to achieve large speedups. In addition, it improves memory consumption. as normally NumPy allocate memory to every single intermediate step, and here it can be avoided. In addition, we can install bottleneck, which uses a specialized non-aware Cython routines to achieve larger speedups. And this optimization is great for medium to big size dataset. So probably above 50K rows. In addition, it's important to understand that you don't need to change any of your code, only to install. The next tip is to utilize compile code. Python is dynamic by nature, and for this reason, there is no compilation optimization that can be achieved, which can cause Python to be slow sometimes. Here is an example of a function that doing some accumulation, and we can see that it takes 40 seconds to execute on pure Python. And we can use Cython and Numba to compile the code either beforehand or on runtime. And I'm going to cover Cython first. So Cython help us to get 100 times speed up from pure Python, but it has a learning curve. You need to change your code and you need to know how to integrate it. It has a separate compilation step, which is both a con and a pro. On the one hand, there is additional work to integrate the Cython code, and on the other hand, there is no compilation overhead on runtime. In our example, we can see that simply we annotate the types. We say that the parameter is long, and here we define the variable using cdef and so on. And we can see that we got to 150 milliseconds, which is 100 times performance improvement over the pure Python code. The next tool is Numba, which can get us to up to 200 times speedups from pure Python. It's really easy to use. You only need to add a decorator, and it's highly configurable. You can indicate the accuracy of mathematical operations, if you want it to work in parallel or not, and so on. But it supports mostly numeric functions, so if you have some smart string manipulation, it will probably not be too useful for you. In our example, we can see that we simply add this decorator, and in runtime it compile this code and execute it. So we can see that we got to 218 milliseconds, which is 65 times performance improvement. So in general, you should first try to use existing vectorized methods, and if there is no vectorized method that you can utilize, you should use Numba because it's so easy. And if it's not enough for you and you want to do some more advanced string manipulation, you can use Cython, and it will help you a lot. Another set of tools and tips that you can use is general Python optimizations. The first one is caching. Caching allows us to avoid unnecessary work and computation, and it will result in faster code. You can use LRU cache, which is in the functools module, which is pretty easy. And next tip is to think about how you allocate intermediate variable. So when you calculate intermediate variables, you save both objects in the same time. So we have the memory footprint of both objects in the same time. So if we allocate the variables smarter, we can save a lot of memory. In this example, I'm loading data, and we can see that here I'm simply creating a variable called data, and here I'm doing some more things, and we can see that it takes a bit more than 4 gigabytes. And here we can see that if I reallocate the same variable, I will get 30% improvement in the memory footprint. Another tip is really to think about concurrency and parallelism. Pandas in general use a single process. And if you are a CPU bound application, you can benefit from parallelism. And if you are IO bound application, you can benefit from both. So I would love to go over the tips that I gave you. And I really believe that if you use them, you will have much better and optimized code. The first is that you should only use what you need. Filter as early as possible the columns and the rows. You shouldn't reinvent the wheel. Use existing libraries. You should really avoid loops. It's a disaster, and it can take your execution time from milliseconds to hours. And you should really think about the types of the columns that you are allocating. In addition, you should install Pandas as recommended in the documentation, and we should utilize compile code techniques. And lastly, there are general Python optimization that we can use. I hope that you now understand that optimizing your Pandas code is not rocket science and that everyone can do it. I hope you enjoyed the talks, and if you have any questions, feel free.